1950, early 1960s. So that's the time period we're sitting in. You don't have like a high capacity computer. You do not have a graphing calculator. So if someone asks you to find like the natural log of 2, like you can't just like pick up a calculator and punch in natural log of 2 and get that decimal. So what did we use to kind of find in math the values of those functions used without a calculator? And we had to rely on approximations. So like, yes, there was things like slide rules, but those were based off of like some math behind them of why they were. And in BC calculus, we actually still kind of learned some of those old methods of approximations. The first approximation that we learned, we kind of touched on it a little bit yesterday. We had the tangent line approximation, where you could use a tangent line to approximate values on the graph, and that's what we're going to start at today. Another type of approximation method we have is Euler's method. And then the third type of approximation that we have, which is going to be like the most exact one, is what we get into next unit with Taylor series and Taylor polynomials. So Euler's method is going to be kind of like a bridge between basically the tangent line and these things called Taylor polynomials. Again, realistically, in today's modern world, like no scientist or mathematician is approximating a function using Euler's method. Like we have computer programs that can do all of that. But we do need to understand the math behind it because it is going to bridge us into this thing that we'll eventually learn called Taylor polynomials. I don't want to discredit Euler's method. Like it actually was used quite often up until like when graphing calculators started becoming real popular around like the 80s. Like it even famously, Euler's method was used to basically get men on the moon. So like it's not like it's some ancient math. Like it was used up until pretty recently. We just have more modern methods kind of now. So like during today's notes, we are just going to kind of pretend that we're like in the 1950s, minus all the segregation and all that, and just kind of just mathematically, like we just can't do with a graphing calculator. So before we get into Euler's method, let's just talk about the tangent line approximation again. So again, we can use a tangent line to approximate a function as long as we're somewhat close to that point of tangency. So for example, looking at the second part of that question, we're going to use our tangent line to approximate the natural log of 2. Again, we are pretending we don't have a calculator that can handle natural logs. We can't just pick it up and type in the natural log of 2. So the idea behind it is if we can do a graph of it, like we know roughly what the graph of the natural log looks like. We know how to find a tangent line. Then we can kind of use that tangent line to approximate a value on the graph. It's not going to be exact, but it can be close enough in certain situations. So going in to find that tangent line approximation, like we know what y prime is. The derivative of the natural log of x is 1 over x. What is then the slope at 1? The slope of 1 is 1 over 1, or just 1. Also, without a graphing calculator, we can figure out what the function is located at 1, because we do know what the natural log of 1 is from just like properties of logarithms. The natural log of 1 is 0. So then our tangent line, I have y minus the y coordinate is equal to the slope times x minus the x coordinate. So my tangent line for this one, chose a pretty simple one, is just y is equal to x minus 1. So again, conceptually, what we're kind of thinking about, close to x equals to 1, the tangent line and the function are like close enough to approximate it. So if I want to approximate the natural log of 2, it's going to be approximately what the value of 2 is in the tangent line. So plugging it into the tangent line, we get 2 minus 1, and 2 minus 1 is 1. Now, obviously, we know that the natural log of 2 is not 1. Like, I live in modern times. I can pick up my calculator and see that the natural log of 2 is exactly 0.69314, ... But just kind of thinking to yourself, like, 1 is close to the natural log of 2. Like, it's not exactly like it, but it is close enough. Other things we often want to do with approximations, again, we talked about this yesterday as well. When you find an approximation, we often want to know if that approximation is over or under the actual value. And how do we determine whether an approximation is over or under if we think about the concavity of the graph and how it would be bending and moving away from a tangent line. So again, if we're looking at the natural log of x, that's again the function that we were kind of approximating. We already said what y prime was. That's just 1 over x, or x to the negative first power. And then y double prime, negative 1 x to the negative 2, which is negative 1 over x squared. If your derivative is negative 1 over x squared, what can we say about the second derivative? What is it always going to be? Concave down. So the derivative, the function is always concave down. The second derivative we know is always going to be less than 0 always, because we have a negative number divided by something squared. So basically we know that our estimate for the natural log of 2, if the graph is concave down, the tangent line is above it. So our estimate is over the actual value. Because the natural log of x is concave down. Why is it important to kind of think about whether an approximation will be over or under? Just kind of think about, like, if you're a scientist and you're having to, like, find some approximations. It's good to know, like, at least if you're not going to be exact with your numbers, if your value is going to be slightly over what it actually is or slightly under what it actually is. Yes?
I know from differential equations, you're not going to know what the graph looks like, but can you just think of what the graph natural log of x
So yeah, so we know what the natural log of x looks like. Real life scenario we'll get to is, like, we will have problems that we don't have any idea what the graph will look like, and that would be a more realistic example of that. So we want to think about, like, so that is an approximation. We already know, so if I go kind of go back to this graph, like, we know that looking at this, we can't get it exactly. Like, the tangent line is straight and the graph is curved. The idea behind Euler's method is, what if instead of doing like a single tangent line, that you can kind of like break that tangent line into like segments and kind of make it bend a little bit better to fit the graph of the curve, and then hence get like a little better of an estimate of what the graph looks like or what that value is. So again, this is all kind of computer generated using my modern technology. This will be an example of kind of where Euler's method is going to come into play, where instead of taking a single tangent line, you'll go to like, you'll first start with the tangent line and then imagine like breaking it, having a new slope, and then kind of keep extending it. We can kind of get more and more exact if you think, like if I broke that to like 4 pieces, it's going to bend a little bit closer to the graph, 5 pieces even closer, 6 pieces even closer. And you can kind of imagine how we'll be able to use straight line segments to better fit a curve on the graph. So the major idea when we're talking about Euler's method is, how do we take that tangent line and break it correctly into some segments so that we can then use it to find the appropriate y values. And to do that, I'm going to go ahead and let's just talk about it. Euler is German, so there's your Guten Tag for you. But when you're looking to do Euler's method, there's 3 things you're going to want to identify. You will always have to have some known starting point, and I'm going to just call that x sub 0 and y sub 0. That's going to be some starting point on the graph. Could be at 0, could be located somewhere else. You're always going to have the step size, which is basically going to be the difference between the x values of these like little segments that we're going to use to connect the graph. Sometimes instead of h, we will use delta x. I actually tend to use delta x a little bit more because it more directly connects Euler's method to like slope and the derivative. And then you'll have like the number of steps, and that will always be provided to you, or you can figure it out based off the information. When I say number of steps, that's going to be like the number of segments you're using instead of just a single tangent line. So if your step was like 2, you'll be using like 2 segments to kind of bend along the curve, 3 segments, 4, etc. Of course, the more segments you use, the more exact your approximation is going to be. But realistically, for us, like we're probably not going to do more than like 4 or 5 steps. It does get pretty tedious after a while. So you're just kind of like punching in numbers at that point. So let's just look at that same example we did, but with Euler's method. And so I kind of chose the same problem. Like we know for a fact that the natural log of 1 is equal to 0. And we're going to use Euler's method to approximate the value of the natural log of 2. And again, you're putting yourself in this mindset that we do not have a calculator that can just pick up and type in natural log of 2 and see the decimal. We will use a calculator for like simple calculations, because they can use a slide rule for like simple multiplication and addition. So we will use a calculator kind of for that. But we're not going to use the calculator to find the natural log of 2. We're going to use Euler's method. And in Euler's method, I always do mine setting up a table. The textbook and even on the AP exam, like on their rubrics and answer key, they do like these weird, like long equations. The table is going to be much more beneficial to you. I do want to talk about this table, and then I'm going to show you how you work it out. So in your table, you are always going to have to show these 2 columns, because those 2 columns are going to show the progression of coordinates at the end of each segment. So you have to show those. To earn credit on the AP exam, it has to see kind of where like each segment starts at and each segment ends at. I always show a version at least of those second 2 columns, but those are really considered scratch work. On the AP exam, I know there were certain versions this past summer that did have Euler's method on it. And when we were grading it, we were instructed only to grade the progression of coordinates, and like we didn't even look at those 2 columns, but those are going to help you kind of fill in the rest of the table. And so looking at these columns and kind of the notation I have on them, so the first 2 columns are basically going to be the progression of your x coordinates. So we'll have the starting x and y coordinate, then where that segment ends, and then kind of keep going down the table of where each segment is starting and then picking up at. This next column, we will know the derivative, like this is in differential equations. We know the derivative is y prime, which is the same thing as saying dy dx. And what allows Euler method to work is it is an approximation. When we say dy dx, that's kind of a reminder that the derivative really is a slope. Well, what did we say slope was way back in the 6th grade? It's the change in y over the change in x. We're going to approximate the derivative in some ways using an old school slope. So we're going to find the derivative. And then this last column is going to kind of tell us, we'll get to that in a second. I don't want to get too far ahead. But that's going to be the table that we use to kind of set up the problem. The delta x is basically what you're going to be going up by your x's each time. And then your delta y, which we see in that last column, is what we're going to go up by on the y's each time. Where this equation comes from, so again, it's pretty easy to see algebraically. If we're saying that y prime is the same thing as dy dx, dy dx is approximately the change in y over the change in x. Logically then, y prime is approximately delta y over delta x. Delta x will be something that will be given. So like if I multiply that on the other side, we get y prime times delta x is approximately delta y, which is what's going to go in that last column. So I'm going to go ahead and like change the slide just to have a fresh screen. I'll like work it out first just so you can see the process, because honestly it's like once you get in a rhythm, like it's just the same thing over and over and over again until you get to the answer. And then I will give you time to write it down. So if you just want to like watch me do it, that's perfectly fine. So we're going to do Euler's method to approximate the natural log of 2. We have a starting point. We know that the natural log of 1 is 0. So that's going to be 1 is my starting x coordinate and 0 is my starting y coordinate. The other thing I fill in automatically before doing any calculations is the steps all the way to my final spot. So it tells me that I am doing a step size of 0.25. That is my delta x value. So my first segment is starting at 1. The second segment is starting at 1.25. The next one is starting at 1.5. The one after that is stopping at 1.75. And then that very last one is stopping at 2. That is where I'm going to stop at because I am trying to find the natural log of 2. So this number that will eventually go here is going to be my final answer. So let's go ahead and start filling in the pieces. Y prime, again, is equal to dy dx, which is approximately delta y over delta x. Well, what is y prime? We know this is the natural log of x, so y prime is 1 over x. So I'm going to go ahead and find y prime. So again, y prime is equal to 1 over the x value, which is just going to give you 1. And then I'm going to use that to help me find my delta y. So delta y is approximately my y prime, which was 1, times my delta x, which is 0.25, which is just 0.25. What do I do with this 0.25? That's delta y. So we already know how far over on the x's we go each time. This is the next step. We go how far up we're going in the y direction. So I'm at 0. Adding 0.25 to that is going to give me 0.25. And then I just repeat until I get to the answer. So again, find my new derivative, y prime. Y prime is 1 over the x value. Could do a decimal, but this one's pretty easy to do with a fraction. 1.25 is 5/4, so 1 over 5/4 is 4/5. So then I want to find the delta y. Delta y would be the derivative times delta x. 0.25 is the same thing as 1/4. Again, a fraction kind of makes my math easier. So that's going to give me 1/5, which is basically just 0.2, right? Yeah. And I just kind of repeat that process. That's my new delta y. Adding it to that y value I left off at, and I'm now at 0.45. And then we're going to repeat that again, repeat it again, and then we have your answer. I am going to pick up my calculator now just to do the little basic calculations, and then we'll kind of see what our answer is. I am going to go back and show this on the graph just so we can kind of see what we actually did. So again, y prime, 1 over the x value, 1 divided by the x value. I'm going to go just switch to decimals. Don't want to round too early. Then I want to do my derivative times delta x. So my derivative times another delta x. I have 0.1666 repeating. That's my new delta y. Add that delta y to the y value that I left off on. And then repeat one last time. Y prime is 1 over x. And then delta y is your derivative times the delta x. And then that's going to give us my delta y. And I'm going to add that to the y value I had. And I get 0. Rounding to, I'm going to do 4 places for that awkward 9.7595. So you can kind of see like these second two columns, like as long as you can follow your work, many of you could probably just like type that in the calculator without having to show a lot of that written down. What will be graded again is the progression of these x coordinates and the progression of the y coordinates. Looking at these, what we have basically found is we now are approximating using Euler's method that the natural log of 2 is approximately 0.7595, which is a lot closer. Like again, using modern technology, the natural log of 2 is 0.69, so you can see that it is a little bit closer. The over approximation for Euler's method is the same as a tangent line. So since the natural log of x is concave down, we knew automatically that this was going to be over the actual value. And again, kind of what's happening, so here's like the math a little bit behind of why it's working. Normally, we wouldn't know what the graph looks like in a true differential equation problem. But what we have found is a progression of coordinates. So we know that 1, 0 was a coordinate on the graph for the estimation. We knew we had this coordinate then that became 1.25 was at 0.25. 1.5 was at 1.45. And then 1.75 was at the 1.616 repeating. And then at 2, we were at 0.75. And then these are straight line segments. So again, it doesn't fit exactly along the natural log curve, but it's definitely a lot closer than what you would have gotten if you used a tangent line. You can kind of see how it bends. So then like mathematically, you can kind of think the more steps you did, the more accurate you would have been. But that's basically Euler's method. Questions on that process? All right, so let's do one that's a little bit more reasonable, because again, we know we can easily type in the natural log of 2 in a calculator. Here's a type of problem where Euler's method is going to be a lot more useful to us. So I have a colony of bacteria. It is growing according to the model dp dt, which is equal to p times 5 minus t. So if I'm looking at this one, since p is up top, p is basically like the y coordinate, and t is acting as the x coordinate. Let me not do that backwards. And so that is the population kind of growth model for this bacteria. Again, looking at this, there's a mixture of like P's and T's. So like we can't easily integrate this problem quite yet. We don't know what this graph looks like. So this is where Euler's method really does become powerful. Like we can't find that function P of T readily right now. So in order to find any like values on the graph, Euler's method is going to be useful to us. So it tells us at 4 p.m. there are 100 cells in the colony, and we want to predict the population at 4 p.m. It will always tell you kind of the step size to use. We're using Euler's method at 15-minute intervals, and we'll finally round our final answer to the nearest whole number. I should have said T is the number of hours since noon. So we know that noon is basically T is equal to 0. 4 p.m. is when T is equal to 4. We know the initial condition is at 100. You'll always have to have initial condition. If you're trying to find what's happening at 4:45, you're basically trying to find P of 4.75. Go ahead and try that one on your own to see if you can get an approximation of how many bacteria we'll have at 4:45 using Euler's method. There wouldn't be a chart provided on the AP exam. If you're looking at OneNote, I just kind of give you a blank one, but normally that would just be completely blank space, and you have to kind of draw the chart yourself. So go ahead and try that one for me. There's definitely more rows than you need. But yeah, go ahead and try that one, and then I'll be kind of towards the end of what I want to get done today. And again, there will be certain things you can always fill in without doing like the math yet. I know where my answer is going to be at.
Could you do 0.25 because 15 is what?
15 is 0.25 an hour, yeah. And I already forgot what the derivative was. So there's my setup if you kind of want to see if you're at least on somewhat of the right track. Again, you have to have your initial condition. The step is basically telling you how far up you're going in the x values each time, which in this case, the x values are t. You use the derivative and that step to basically figure out what the delta y is, in this case, delta p, and then show your progression of the y coordinates, and then that will be your answer. And it does say round it to the nearest whole number, since we are talking about bacteria. One thing that does kind of suck about Euler's method is if you mess up in one row, then pretty much everything after it is naturally going to be incorrect. So you do just want to be careful as you're typing things in. And again, you wouldn't have to show necessarily all the work in the second two columns, especially if you're just kind of punching it into a calculator. I'm just showing it just to kind of make myself be a little bit organized with it and just to kind of show you as well the steps. So there's my work with my answer. Again, once you sort of get in the rhythm, like it just kind of goes straight down. So we are starting at 4, 0, and we know that to find delta y, which in this case delta p, is going to be the derivative times your step size. So I plugged it into the derivative. This one we did plug p and t into the derivative, multiply by 0.25. The delta p is going to be 25. Add that to the y coordinate we started with. So my new y coordinate is 125. The new t value is 4.25 from the step size. Repeat that process, plug it into the derivative, multiply it by the step size. You have delta p. Add that to the previous y coordinate. Repeat, add that to the y coordinate. What I have highlighted in green then would be our approximation at 4.75. Again, that's not the exact one. That's like us using, in this case, 3 segments to kind of approximate it. And we can now predict that at 4:45 p.m., there are approximately 167 bacteria. Questions on that? All right, so we are kind of benefiting from living in the modern age. So here is the computer-generated slope field for that differential equation. And that's what the graph looks like. We don't know again exactly what the graph looks like, but that is the slope field of it. What Euler's method has told us, I'm going to zoom out pretty far so I can see my answers on the same slide. This will scroll, there it goes. So we're started at 4, 100. We knew that was an initial condition. At 4.25, we were at 125. At 4.5, we were at like 148. 1.8, and then at 475, it was like 1.66. So again, we don't know what the graph looks like, but through Euler's method, we're kind of creating this like jagged edge of the curve. So then we have that approximation of where it would be located at. So that is Euler's method. Again, that really is all there is to it. So you definitely just want to kind of get used to that like process. I did say that this was used to get men on the moon. So we are actually going to watch a little video clip. Those of you at home, my sharing a screen and playing sound is not working. So I'm going to post the video in the chat, and I do kind of want y'all to watch it. So it's posted there now. How many of y'all have actually seen Hidden Figures? Right, we've seen Hidden Figures, maybe need a background of it.
I have seen it.
Okay, so like good background, like clearly kind of a nice Black History Month. So like this is getting men on the moon. Mainly African American women were serving as their official title was calculators. And that's not because they were using a calculator, like they were the calculator, doing all the number crunching while the mainly white men scientists were claiming all the credit. This is Hidden Figures based on a true life story. The actress Taraji is playing Katherine Johnson, who actually just passed away almost exactly a year ago today. She was like 90 something, but she was one of the lead calculators, again, the human calculators doing calculations, credited with really kind of coming in behind these scientists who like were stuck on a problem and being like, hey, dummies, I mean, she definitely didn't say that, but hey, dummies, let's just do Euler's method because it works, it's old math, but it allows us to get close enough. Obviously, she was not probably doing a step size of like 4. They are landing a whole structure on the moon, but it's kind of fun to see. So yeah, here is your Euler's method content of the day.
The problem is when the capsule moves from an elliptical orbit to a parabolic orbit. There's no mathematical formula for that. We can calculate launch and landing, but without this conversion, the capsule stays in orbit. We can't bring it back home.
Maybe we've been thinking about this all wrong. How's that? Maybe it's not new math at all.
It could be old math. Something that looks at the problem numerically and not theoretically. Math is always dependable.
For you, it is.
Euler's method,
Euler's method.
yes.
But that's ancient.
But it works. It works numerically.
That's it. Let's type it up.
But yay, Euler's method. On another note, this is just me going to be like teacher kind of bragging moment.
We hope you will enjoy the following ranking.
No.
Please let us know your...
No, thank you.
I enjoyed it.
But, thank you. The other thing I did want to show you, again, this is just not anything really related to class. But while we were talking about landing on the moon using Euler's method, how many of us pay attention to news? We know that NASA just landed a rover on Mars. So my like proud teacher moment of that, this is Brianna. I taught her kind of a lot like y'all in pre-calculus and calculus. She is a senior at Georgia Tech now, interned with NASA last summer, but she actually, as part of her internship, went and like double checked the math to get the rover on Mars, which I like saying like, can't take credit of that, but I like to think, I taught her pre-calc and calculus, so like,
You're essentially-
maybe a small part of me helped get the rope on Mars. It's definitely all Brianna. But yeah, math can help us do big things, right? So yeah, there's just your inspirational story of the day. What you can go ahead and start working on. Sorry, not as exciting about getting a rover on Mars, but you can go ahead and start homework 2 if you haven't already. So I'm gonna add homework number 2 to the checklist. When you are looking at homework number 2 with Euler's method, I highlighted certain questions and made some of them optional because I do think Euler's method gets super repetitive after a while. So skip the ones I say are optional unless you just really need to hammer home how to keep plugging things in and multiplying. Definitely, like if you're at home, stay behind if you have any questions. But Monday, of course, we'll kind of regroup and just keep moving along.